Okay, thank you. So, hello, and let's get started. So, as introduced, I'm Ants Aasma. I'm a lead database consultant at Cybertec, Postgres contributor, but maybe most relevant to this talk that I've been working at Cybertec, helping other people run Postgres fast for 13 years now, and we've seen quite a lot of explain plans in that time. So all of this that's going to come is based on experience from the field. But first I have to thank a couple of our partners here. One of them would be Open Source DB, that is our partner in India. So if you need any help collaborating with Cybertec, talk to them. And also ReadySet, who are doing query caching done right. So talk to them if you want to make your database faster. But I'm going to get quickly started here because this talk is going to be long. And we're going to be talking about explain. Hopefully most of you have heard about it. So what explain does is it tells us how does the database plan to execute our query. And we can then run explain analyze, and the database will collect information and tell us did the plan work well or did it not work well. And if you want even more information, then we can add a bunch of stuff in there. So we can add verbose or get the settings used or number of buffers accessed or write-ahead logging information and so on. And yeah, maybe it's time to have an explain everything command because this, I couldn't even fit it on the slide, all of the options that we have available today. And you will see we will need more. So what's this talk going to be about? So explain is really great. So I hope most of you have used explain. So raise your hands if you are familiar with explain. And keep your hand up if you understand it well. Yeah. Explain is something that is a really deep topic, so I'm not surprised. It's a full day training to understand explain, and even then you will only scratch the surface. It's a lifetime to learn it properly. But it really is a great tool, so you should be using it. But this talk is where it's not yet great. We're going to be talking about stuff that doesn't work so well. So warning for you, this talk will have some code in it. So if you are offended by code, be warned. And there's going to be a lot of it. And in some cases, it might be a bit small. So if you have trouble seeing this one here, you might want to try to get closer or get the slides. They will be available on the conference website, but the previous version of those slides are available from PGConf site from 2024. So you can get them from there to follow along. And you should be able to run most of those examples by just copy and pasting from the slides. But just to get everybody on the same page, I will do a really quick crash course on how to read explain plans. The explain plan represents the database's internal volcano execution model that Amit was talking about yesterday. It's called the volcano model because it's wide at the bottom, narrow at the top, and the rows come out of the top. So that's why it's a volcano. So here I have a simple query that does a join, has a where clause and a limit. And the explain plan for this will look something like this. There's going to be a bunch of nodes. At the top there's a limit. Under it there's going to be a nested loop. And then there's a sequential scan and index scan node. And sequential scan just reads the whole table and throws away rows that it doesn't care about, whereas index scan will read some of the rows from an index and then fetches them from a table. The stuff that we are interested in is the cost here. There are two numbers that might be somewhat confusing what those do, but the important part is the second number, which is the planner's estimate. How much time will this thing take? The tricky part here is that the unit of time is actually not anything real. It's just an arbitrary unit. So it's not milliseconds, not microseconds. but hopefully it's at least somewhat correlated to the actual time that it will take. And the first number there, that's just going to be the time it takes to fetch the first row. And that one we will need for cases such as limit, where we know that we don't need all of the rows. And you can see that also here, that we are planning to fetch from the join 480 rows, but because we have a limit, we know that the limit will not need all of them. So that means that the total cost will go a bit down proportionally to the limit compared to the total rows that we are expecting to get. So now let's try to run this query. So let's run explain analyze. And this again doesn't fit on the slide, but because the cost information we already talked about, let's get rid of that. We can turn costs off and make it slightly easier to read on the slides here. So if we add analyze, we will get an additional entry in there with the actual information, so what it actually took. And in that case, there will be this time entry here, and that means how much time did this node take. There's a total execution time also at the bottom that's going to be like 0.3 milliseconds for this whole plan. And the limit at the top here took 0.279 of that time, and it's inclusive of everything that happens below it. So that's how you interpret those numbers. And again, the first number is just the time for the first row. And if you can see here, the actual rows will be how many rows were actually fetched. So the nested loop would have produced about 500 rows, but because we only needed 100, we only fetched 100 from it. And we also have some extra information about some interesting stuff, like how many rows were discarded by this where clause that we have on this sequential scan here. And the final part about the explain plans that I want you to understand before we move on is buffers. This will tell us how many database pages were accessed to answer your query, and how many of them were being read from the operating system. And it's typically you will see this shared entry, which means it's from the shared buffers, and hit is how many were in cache, and read is how many were from the operating system. And again, they are inclusive of the node below them. And what else to know is that you should probably make track IO timing be on, because that will give you the useful information about how much time it took. Because the read means a read from operating system, but it could still not be an actual disk IO. It might be coming from the file system cache, which means that it's really fast. And to distinguish between those two, right now the only useful tool we have is track IO timing, which will tell how much time it took. In this case, we can see 2.7 milliseconds to read those 2,000 pages. But anyway, we should at least now have a general idea of what to look for here. So we can move on here. And our first topic will be about toast. To talk about this, we need to understand what a schema, so we can execute some queries on it and understand what they do. I have like a sample dummy application here. We are collecting some reports. It has an ID. We have a rule set that we apply to it, and we collect this in a modern schemaless format as JSON-B, where we have a data document containing a bunch of metrics that have some values. So we have like a metric 1 has a value 0.42 here. And then we have a bunch of rules. So we have a rule ID, rule set ID, then a number, and then which field does it apply to, and what is the maximum value of that field. So this rule should mean that we want to verify that this field is less than this maximum value. Simple dummy application. And for good measure, let's have some indexes also on the rule set ID, because we want to join on this stuff. And also, we need some data to actually have a useful explain plan. Let's create 10,000 reports. Each will have 1,000 metrics in it with some random values. And we will also have 100 different rule sets, each having 10 rules. So the amount of the data altogether will be about 316 megabytes. Each document itself is 32 kilobytes, which will be important later. And the total table size is somehow smaller. Also, we'll discuss that later, how that can be. So let's read this data and see how quickly can Postgres do this stuff. So we will explain analyze and simple select star from those reports. And we will get it back in 0.9 milliseconds. Postgres is really fast, right? And actually, that might be a bit too fast. If we run the numbers, that's 300 gigabytes per second. That sounds a bit suspicious, so let's double check this number. Let's use PSQL's timing functionality and run this in PSQL. We turn timing on, then we copy the output of that query to device null. We can see we got 10,000 rows, but this time it took 1.7 seconds. This seems more reasonable. So what's going on? So what happened is that those larger values that we are storing there, those 32 kilobyte JSON values, they are split up into chunks and stored in a secondary table, because one row in Postgres can only be on a single page. And if you want to store values that are larger than one page, we have to split them up. And this mechanism is called toasting. For each table that might have large values in it, there will be a toast table in Postgres where there are those smaller chunks stored. And in the main table in the row, we just store an identifier that points to that other table and says, if you want to read this value, that's going to be value number 123 in that toast table. And if somebody needs that value, this is transparently fetched from the toast table, and this is called detoasting. And when we ran explain analyze, we didn't actually need this value because we were not sending the output to anywhere, so we didn't go to the toast table. We were just reading all of those toast identifiers and then throwing them away. But if we send the data actually out, we need to serialize it, and serializing it will trigger this detoasting, and this will actually go and read the actual data. Now, good news is that this is one of the things that has been already fixed in explain. Starting from Postgres 17, we can do explain serialized text, and this will then serialize the output and calculate how much time does it take. It still doesn't measure how much time it would take to send it out over the network, but at least we can see that it would take 1.1 seconds to serialize it. And we can see that we have those 300 megabytes here. The fact that toast is somehow involved in here is nowhere in this explain plan. So this is why explain is not telling you anything about it. This is completely hidden from you. So you have to know that this is something that might be going on within this serialization. It's not only the calculation, but it might also be detoasting. But output is not the only place where we can have detoasting in a plan. It can be anywhere. Here we have a query that joins our reports with our rules using the rule set ID. And then we'll have check, does this report exceed our rule? So is this an invalid report? But we only check the rule number 1. We don't talk about why, but yeah. So let's run this query and see how much time does it take. It takes altogether 300 milliseconds. But if you look at the total time, it's spent here running this merge join. But the nodes under this merge join are 2 index scans, and those are 0.3 milliseconds and 3 milliseconds. Those are fast, but the join altogether is slow. And another hint of what's going on is the buffer numbers here. So the index scans are accessing some buffers, but the total number of buffers accessed by the merge join is a whole lot bigger. So why is the join so expensive? The trick is in this join filter condition here. So this join filter accesses the data field, and it actually needs to detoast it. And this is done while we are doing this join. and this will take the time there. But it gets worse. Detoasting is not cached. So here is the same query, but we exclude this rule number clause. So we are checking it for all rules. And this time it's taking 2.5 seconds, and we are hitting 400,000 buffers. One buffer is 8 kilobytes, so that would mean that we are reading 3.2 gigabytes to answer this query. That's quite a lot. It's about 10 times bigger than the data that we have. That 10 suspiciously matches the amount of rules that we have. And what's happening here is that every time we need to evaluate this join filter, we go and fetch this data field, we evaluate the rule, and then we throw it away. And then the next rule comes in for the same field, and we repeat. So there is no caching for those values. So how to find these types of issues in real plans? And explain doesn't help us too much, but the things that you would be looking for is if you have some unreasonably high buffer accesses in some places, that will give you a hint that something fishy is going on over there. And also keep track of where do you have large values in your queries and how do they move through the plan. If you add a verbose field to your explain query, you will see which values are being output from which node, and you can track where is the first detoasting happening. So here's another example of early detoasting. So that's another way that detoasting can go bad. Here we are looking for the length of random 100 rows. So we order by random, limit to 100, and then take the length of the field. It takes 1.3 seconds, and we are accessing all of the data, and we need to sort about 4 megabytes here. And the reason for this is that we are actually detoasting immediately after we find the row. We detoast the data value, and then we sort it, and then we limit it. So how to fix this type of stuff? So in this case, we were detoasting too early. We were detoasting and then throwing the value away because it was not in the top 100. But to get rid of this, we can use some tricks with subqueries and offset to create the boundary over which our evaluation clauses cannot move up or down. That's some specific terms, so better to do an example. So instead of selecting from reports, this length thing, we only select the data from it, do the limit, and then outside of this subquery, we execute the length check. So we made our query more complex, but if we check the execution plan, it's now, 100 times faster. And we, over here, are outputting only the data field, which means that no detoasting is necessary, and we only need a bit of stuff to sort it. And then only on output are we actually executing this detoasting code. So that was the case where we are doing this too early. The other case is when we are detoasting too late, and we are doing it multiple times. And to fix that one, we can force early detoasting using a dummy operation on the data. So taking our previous query here, we need to do a small little change. So instead of selecting from reports, we select from reports in a subquery, add an offset. And the important part here is for the data field, we do an operation that forces detoasting. In this case, we just add an empty value to it. It doesn't change the data, but Postgres doesn't know that, so it cannot optimize it away. And if you do this, previously this ran for 2.5 seconds. Now we run it in 300 milliseconds because we only need to fetch detoast the values once. So to recap, how do you handle toast in queries? So you need to be conscious about, do you even need to worry about this? If all of your columns are ints, you don't need to care. But if you have some like megabyte-sized JSON documents or some text fields that are huge, then keep track of where are they used. And know that the Postgres planner is not your friend here. The Postgres planner has no idea about detoasting, and actually even worse, because the statistics think that the detoasted value is small. It even has the wrong idea about the cost sometimes. But once you know where the detoasting, that detoasting is happening, think a bit about, do you want to be eager or lazy? Are you throwing rows away, or are you using one row multiple times due to a join or something? And then use the tricks I showed you here to just force the planner to not do anything stupid. Okay, but that's it about toasting. Let's move on to another topic, visibility. For this one, we need a different schema. So let's build quickly a task queue, a message queue type of thing. So we have a task status type that we can have a to do, done, or failed for a task. There we have an ID, job ID, then a status field. When was this task added, and is it done or not? And because we will be mostly caring about stuff that is not done yet, let's add an index on tasks that are in the to-do status, and let's order them by the added field because we want to start from the oldest first. And generate some data in there. Let's add 100 to-do tasks. And then, because this is about visibility, we will need an active workload to make it actually work. So over here we have a workload that is consisting of 2 queries. One of them is adding a new task, and the other one is completing a task. So it's selecting from tasks a to-do one, and it's ordering by added, and taking via limit 1 the first one. So it's basically picking the first task. And it uses a good Postgres feature called for update skip blocked. So if somebody else is currently updating that task, we will skip it and pick the next one. This is, the query itself is fine. This is how you would build a task queue in Postgres. So let's run this workload. We use PGBench to run it. PGBench can take SQL scripts. So with a -f, you can give it your custom scripts, and then you can tell it, let's run this at 2,000 transactions per second, and using 8 connections, and we want to see your progress every 10 seconds, and run it for 10 minutes. And this is what the output will look like. Every 10 seconds you will get a summary of what's going on. We can see that we are basically keeping up with the workload, about 2,000 transactions per second, everything is working fine. But now there's a business analyst that is using a tool that is notorious for leaving transactions open, and they are running this transaction where they select the count star from the tasks, and then they go away and has a coffee to think, is that count the correct number or not? But this leaves the transaction open. And now what happens with the benchmark is that things go south pretty quickly. Within 2 minutes, we are already a minute behind. And the transactions per second rate is falling and falling and falling. So if this were a real system, this is when we will get this call that help, the server is on fire, can you make it work now? And because we are a good operation, we will have PGStat statements monitoring set up with PGWatch, and we can check it to see that the reason that we are slow now is that the queue completion query is 100 times slower. And what do you do when you have a slow query? You get the explain plan. So let's do that, and we will get this kind of explain plan. We will see that we are executing it in 25 milliseconds. And basically all of those 25 milliseconds are spent in this index scan to get 10 rows. Why 10 rows? Well, that's this skip lock thing. We are just skipping over some rows that somebody else is looking at. And we are filtering for the do task status. And to get those 10 rows, we are hitting 95,000 pages to find 10 rows. So what is going on? What's actually happening is that because of the open transaction, our auto vacuum cannot clean up the completed jobs. Those will be remaining in our table, and we will have to use our transaction isolation to figure out which one of those is visible to us and which one is not. And even worse, there is a method in the index where we can mark an entry in the index as not visible to anybody. So if somebody goes and looks up a row from the index and finds it to be dead for everybody, then they can go back to the index and mark it as not visible, as killed. And the next person that comes along and looks at this row in the index, they can just skip it because they know that it's not visible. But because there is one backend that can still see this row, we cannot kill it yet, and that's why we need to keep it around. So every time we want to see the oldest to-do task, we have to look at every one of those tasks that were completed since this transaction opened, go and read the row from the table, see, okay, this is not visible to me, go back to the index, find the next one, go to the tables, fetch it, and so on. And this takes quite a bit of time. Luckily, the fix is simple. Well, here, this stuff is not visible in the explain numbers. We only see that it's taking a lot of time. But to fix this, the fix is simple. We just kill the query, and everything should go happily. So ideally, we would actually even avoid mixing long queries and this heavy update workload. And to enforce this, we have some settings in Postgres where we can enforce some timeouts. So in case somebody forgets a transaction open, we can have Postgres automatically kill it for you. And Postgres 17 also has transaction timeout that limits the whole transaction if there is something that is doing some small queries for a long time. But after we terminate this naughty connection, the first one that will fetch the oldest task will mark all of those index tuples as killed, and the next one is us. We still have to look through the index, scanning a bunch of rows in the index, but it's still only 500 pages, and we can do this in 0.3 milliseconds. And after a bit of time, auto vacuum will clean up the index too, so everything will be nice. So what was missing from the explain? Ideally, we would like to see how many rows did we look at, but decided to discard because they were not visible to us. If we were using this index kill tuple thing, how many rows could we skip fetching it from the table because we know from the index already that it's dead. And this information is not only for index scans, it's also for sequential scans, but it's usually not as bad in the sequential scan. But not yet done with visibility maps here. I want to now talk about a different topic, and for that one we will need a slightly bigger table. We will create 6 million rows, each 100 bytes, so about 600 megs. We have a number and a filler field, and we will create an index on the filler and vacuum analyze, so we can use an index-only scan. And then we just select a number. And Postgres decides to use an index-only scan to fetch it, because the index is way smaller than the table itself, and everything is visible to everybody. But this index-only scan is working correctly. We didn't have to go and fetch anything from the table, but for whatever reason, the number of buffers that we hit is 6 million here, and it's taking about 900 milliseconds to fetch this stuff. So what's happening? So how index-only scan works is that because Postgres doesn't have any transactional information in the indexes, to know whether we can return this row or not, we have to know, is it visible? So we can either go and fetch the row from the table and see the transactional information, but to make it more optimized, Postgres has a way to mark some regions of the table as visible to everybody, and we can use this visibility map to see that can we skip this lookup. So we take the number of the page that the row is on, we calculate on which visibility map page it's on, we look up this visibility map and check the bit, and if it's visible we can immediately return it and skip the table lookup. And this happens for every row. But because doing this buffer lookup, this means we need to do a hash table search to see where in the cache is this visibility map page. This is a bit expensive, so we remember which visibility map page we were looking at last time and where was it. And if we need to check that same page again, we can just check is it still in the same place, which is very likely. But I constructed this example in an evil way so that this caching never works out for us. And this is because one visibility map page covers about 256 megs of a table. So if the table is much bigger than that, then the access will not be correlated. So what can we learn from this is that there are caches everywhere. And because there are caches everywhere, data locality is really important. If you access data together, store it together. And you can use tricks like cluster, fill factor, and other things to make sure that your data is stored in an order that matches how you are reading it. In this case, we can just run cluster command and see that after we run this cluster, the number of pages that are visited is way smaller, and it's about twice as fast. Well, this is admittedly a toy example. In reality, this is not that huge of a problem, but still a nice benefit here. Okay, and finally, let's go on to index conditions. So let's take one of those examples we had earlier, this task queue table. But now we have a new query. We want to find for a job all of the tasks that were added before some timestamp, and we want to get them in ID order. And we need to figure out what is the index that we need to make this query fast. We can consider a couple of different things. We definitely want the job ID in there because that's what we are going to be filtering on. And we might want to have the ID in it because we are ordering by it. And we also might have the added because there is a where clause on it. But what order to put them in the index? Here are two examples of doing it. In the first case, we have the job ID, then an ID, and added. This one runs in 1.2 milliseconds and has 300 buffer hits. And another one, we just switch those two columns around, and this makes it almost 100 times faster. And if you look at the index condition, how is the index being used? This information here, it's identical. So why is one so much slower and one is faster? And the trick here is that when we are doing index range scans, range scan meaning that we are looking for a range of values. In this case, everything below some timestamp. We can only use this if all of the previous columns have a constant value on them. If it's not, then we cannot actually use the index to narrow down the search space. And the intuitive way to think about it is that the index is ordered by the columns. So it's first ordered by job ID, then ID, and then added. And this means that for each job, the ID values will be ordered, but because each ID is unique, then the timestamps are not ordered in any way. We cannot make use of the index to narrow down the search space. But we can still use that value. We don't have to look at the table to filter out the values that are not interesting. So we can use this added column, but just not to narrow down the search space. So we are basically doing a sequential scan within the index. But the problem here for us is that the fact that this added column in one case is used to narrow down the search space, and in another case it's used to just filter stuff out. It's not visible anywhere in the explain plan. And we do not either see that how many actually index entries did we look at, and how many of them were thrown away without returning them. There is a rows removed by filter column in your explain plan, but this will only include the rows that were actually fetched from the table and then thrown away. The stuff that we skipped from the index is not shown. So that's it. What did we learn? Well, explain still doesn't explain everything. Detoasting, bloat scanning, those are things that might make things slow, and hopefully we can make explain a bit better soon. So we saw that some things were fixed in 17. Maybe we'll have some new stuff in 18, and maybe even more stuff in 19. Thanks for your attention. I think we have a few minutes for questions.
Hi, and I have one question. So related to Toast. Before, I think Toast was introduced around Postgres 12 or something. I don't remember exact version. Before that, how Postgres was storing the value which is bigger than the page size? That is my first question.
That's a good question, because I feel myself as old, but not that old. That was before my time. I suspect that we didn't store bigger values then.
Okay, so like what data type Toast is specifically applicable for? For example, JSON-B is an example that you gave. Any other data type which will get toasted or not?
It's applicable to all variable length data types. So that would be text, JSON, arrays, pretty much anything that can change its length. I'm not sure if you can make a numeric value as big to get it to toast, but that's also possible.
Any other question?
So the question was about if the planning time is bigger than execution time. That can be due to multiple things. One is the thing that reading the statistics from the system catalogs can take a bit of time. And another thing is that in some cases we are looking at what is the largest value in an index. So for example, if we are looking for some new stuff, something that is 5 minutes old, the statistics will not be updated with data, but we probably want to know what is the highest value in that table. So the planner actually goes and opens the index and checks what is the biggest value there. So those index probes are also not visible in Explain. Those were in my bonus content as extra stuff that might be in the next talk about what Explain is not telling you. But unfortunately, and it's not visible really what's going on. That's another area to improve. All right. If no more questions, then I will open up the stage for the photo opportunity here. Thank you, everybody.
Yep. Thank you so much.